Hello, I am Alex, and together with my colleague Greg, we are going to present to you Deinsum. Deinsum is a framework for automatically distributing multilinear algebra kernels expressed as tensor contractions in Deinsum notation with a practically I/O optimal schedule.
When we look at modern scientific applications, whether that will be particle physics or quantum simulations, whether on climate modeling, maybe solid state physics or machine learning, what do they all have in common? Well, if we look from the bird's eye view, we'll see that, well, they all share groundbreaking science, solving our world's greatest problems with energy, maybe preventing natural disasters, or even entering domains like art. But also, when we look deep under the hood, we'll see that actually mathematical and physical models that constitute these applications, whether that be, for example, particle in a cell simulations or random phase approximation, maybe phonon interactions in a grid or forward and backward passes in neural net layers, well, they all have performance critical kernels that can be expressed either as, for example, sparse matrix vector multiplication, maybe tall and skinny multiplication, maybe batched matrix multiplication, or some longer contractions of vectors and matrices. So all of these performance critical kernels can be viewed as taking two or more inputs. For example, here we have one input, a matrix, another input, which is a matrix, and then taking pairwise these elements of these inputs, multiplying and then summing or contracting over one or more dimensions, forming this Cartesian iteration space. And then we go layer by layer, forming our output. So all such computations can be succinctly represented by taking the first matrix, first input, which is projected on this ij plane, and we write ij. Then we take another input, and this another input matrix is this projection on this jk plane, and the output that we write after the arrow is this matrix that is projected on this ik plane. So we write ik after the arrow. And what we see here is actually our familiar classical matrix multiplication. So what we see here on top is what is called Einstein summation notation, Einsum in short. So in this work, we examined plethora of different Einsums, ranging from just classical matrix multiplication to tensor and matrix chains to higher order tensors that are crucial, for example, for quantum circuit simulations. And we compared their distributed performance against state-of-the-art libraries and tested on a Piz Daint supercomputer. We measured up to 19 times speedup over the state-of-the-art distributed libraries, achieving the speedup in every single case that we tested. And now Alex will tell us how we achieved this result.
The workflow of Deinsum is as follows. We start with our program described as a Deinsum string. We then split the program to binary operations. We do that because we want to take advantage of associativity to minimize the total number of operations. Next, we derive communication optimal schedules using the SOAP data movement model. SOAP stands for Simple Overlap Access Pattern, and Greg will make an introduction later. Now, SOAP finds for us the optimal tiling parameters, as well as which operations we have to fuse together in order to further lower the I/O of the program. We use the SOAP-derived schedule to distribute the iteration spaces and data of the program in blocks, and the final step is to automatically generate Python code that implements all of the above. And then we use the data-centric framework to compile this code to a shared library. As we will see later, with this workflow, we can achieve up to 19 times speedup over state-of-the-art, and we can support CPU and GPU architectures. So let's look at this workflow in more detail. And to do this, we are going to use a specific example for the rest of this presentation. It's the Deinsum that you see now on your screen. It has 4 input tensors and 1 output, and it uses in total 5 indices, I, J, K, L, and A. Now, the naive way to implement any Deinsum is with a multi-level nested loop, where we have a for loop for each one of these indices. Now, if we look at this example, we basically have 2 parts. The first one, which involves the inputs x, a, and b, is the matricized tensor times Khatri-Rao product, in short MTT-KRP, which is used a lot in the CP decomposition. And the second part is multiplying this temporary output with the matrix C for a matrix-matrix product. Now, if we look at the total number of operations for this naive implementation, we will see that this is approximately equal to the product of the ranges of all the for loops. Now, in the second step, we split our program to binary operations in order to minimize the total number of hops. For our particular example, we split it to 3 binary operations using the Python module opt-Deinsum. The 3 binary operations that our program has been split into are the following. The first one is a Khatri-Rao product, a special case of an outer product. The second one is a tensor dot product, and the last one is a matrix duplication. Now, if we look closely, we will see now that each of these operations depends only on a subset of the indices of the original program. So the first one depends on j, k, and a, the second on I, j, k, a, and the last on I, l, and a. If we add them all together, we will see that asymptotically, the total number of ops of our program after we split them to 3 binary operations depends on only one of them, the tensor dot operation. And therefore, we got a great improvement in the total number of ops compared to the naive implementation. But what about communication?
Okay, so after we minimized the number of arithmetic operations, now it's time to minimize the communication while executing these operations. So minimizing communication can be viewed as maximizing data reuse, and this in turn can be broken down to 2 pieces: data reuse within a kernel using techniques like tiling, for example, and data reuse across kernels using techniques like kernel fusion. So let's see how Deinsum achieves both these objectives on our running example. So what Alex just showed us is to minimize the number of arithmetic operations. First, we break this contraction into 3 binary contractions, and let's examine them one by one. So the first one can be viewed as these 2 matrices multiplied and forming this order 3 tensor. Now the key observation here is that these elements of the first input are used to compute all these outputs, and similarly, these elements from the second input are used to compute all these outputs. Now the assumption is that the inputs are just too big to fit in our local memory. So we can store up to S elements at once, where S is some parameter that corresponds to our size of our local memory, whether that would be a cache or scratchpad or a local memory in a distributed setting. And now we need to decide which elements we want to store to maximize its reuse. And maybe actually natural observation would be to divide this 3D iteration space on a bottom to these regular cubes. And actually, then we can show that the optimal size of this cube would be this square root of our fast memory size divided by 3. And in this, so if that was a matrix multiplication, then that would be actually a provably optimal schedule that was proven in the SC conference in 2019. But actually, the interesting thing is that this is not a matrix multiplication, because we don't need to do this contraction over one of the modes. So we don't need to keep any intermediate results that would pollute our cache or fast memory. So In this work, using our framework, we prove that actually the communication optimal schedule would load this one vector, one row of the first matrix, and then just a single element of the second matrix, and then stream through this surface, maximizing the data reuse. And now if we want to generate a parallel schedule, then the parallel decomposition would slice this iteration space into these horizontal slices. And now if we compare it then with this schedule, for a single load operation, we can perform up to S arithmetic operations compared to this cubic partitioning that would have just a square root of S divided by 2 arithmetic operations per load. So this is actually an asymptotic improvement. But now we can look at it even further. So let's take another our binary contraction. And if we examine it in a separation, and our operation is just to contract these two order 3 tensors, then this can be viewed as just a batched matrix-matrix multiplication. So we go slice by slice, and for each slice we perform a matrix multiplication and we do the reduction. So we have two contractions over J and K, and treating it as a batched gem operation, the optimal schedule would take again our square root of S divided by 3 tile size, and we'll get this square tiling of the iteration space. But the important observation is that this left order 3 tensor is not an input, it's an intermediate result of the previous operation. So what can happen is that actually we can stream the output and pipeline them to the computation. And now if we see this as a single ternary operation like this, then we can actually show what we do in a paper, we show that the actual communication optimal tiling would load this rather exotic rectangular tile of the first matrix and similarly to the second input matrix with the sizes cubic root of S and cubic root of S squared divided by 2, would load this small cube of this order 3 tensor, and in a one operation would produce this rectangle of the output matrix here. And what we are seeing here is actually a MTTKRP contraction, a very important contraction used in many tensor decompositions routines as one of the performance critical steps in the decompositions. And in this work, we establish new tight I/O lower bound for this kernel, which is Q is a minimum number of I/O operations, is 3 times the size of the iteration space divided by the S to the power of 2/3. So compared to a standard state-of-the-art approaches that use gem calls to perform MTTKRP, this is actually an asymptotic improvement over gemming the tensor contractions. To achieve this tight I/O lower bound, actually it takes quite a lot of mathematical work to prove the correctness and tightness of this result. And for that, we use simple overlap access program data movement model. So first we need to examine all possible iteration spaces and possible tilings. Then not only the sizes of the tilings, but also the shapes, because it is not immediately clear that actually the rectangular tiling would be the best. Then we need to examine all possible kernel fusions and check which of them can reduce the data movement. And finally, applying this model specifically to the MTTKRP, we achieve our new tight I/O lower bound. But I don't want to go into details of this, but all the details can be found in the paper. Now the last contraction is just a standard matrix multiplication. Nothing very interesting happening here. So actually the best thing that we can do is just use optimized gem call, and we'll have our square tiling of square root of S divided by 3 with one contraction over A. So using our Deinsum framework, we automatically obtain communication optimal tiling for a single kernel, optimal kernel fusion, and also parallel data composition, which tell us how we should distribute the data in a distributed setting for any given input INSA.
So based on SOAP, for our specific example, we have to group the binary operations into two groups. The first operation has the Khatri-Rao product and the tensor dot operation, making up together the entity here P, while the second group has only the matrix multiplication. Now let's see how we can use the information that we get from SOAP in order to actually distribute our program. Now for every group of operations, we are going to create a Cartesian process grid that is going to have as many dimensions as the iteration variables that are used by the group of operations. Now, in our example, we start with the first group that is using I, J, K, and A, and therefore the corresponding process grid is 4-dimensional, and we use capital P for the extents of the grid and small p for the coordinates. Now the idea here is that every small block of this grid is the computation that is going to be assigned to a particular compute unit or a process. And we can compute the size of the block basically by dividing the sizes of our program with the extents of the process grid. Utilizing the process grid with all its variables that we just introduced, we can rewrite our program from the perspective of a specific process. So now, for example, highlighted, we have the expression for the process local slice of x for a particular process in global coordinates. And with this expression, we can perform the whole computation that belongs to a specific process. Now, the problem here, of course, is that with all these variables, the expressions become a bit complicated and they are not so easy to parse. So most of the time we don't use the global view, but instead we use the local view. In the local view, the expressions are simpler because we don't involve the process coordinates anymore, but only the extent of the process grid in order to compute the size of the block that is assigned to a process. So we can see here that again we have the process local slices of the data and the iteration spaces, but in local coordinates. Now, because we are interested in distributed computing, eventually in our code generation, we are going to use MPI. So for people that understand MPI syntax, we can implement this at a low level with MPI Cartesian communicators. And of course, we also have the second group, which involves the matrix multiplication. And for this, we are going to generate a 3-dimensional process grid. Now, to proceed, let's look at a more specific example. So as we mentioned earlier, SOAP is going to give us the optimal tile sizes from which we can derive the extents of the process grid. So in this particular example, let's say that we want to use 8 processes. That means that for the first group, we get the optimal I/O with a process grid with extents 2, 2, 2, and 1. Essentially, this means that we have a pseudo 3D iteration space, and that's because the 4th dimension has a size of 1. Now, what we can do for each block, we can annotate an ID and the coordinates of this block. And essentially, since we have 8 processes and 8 blocks, this ID is going to be the process ID and the coordinates are going to be the process coordinates. So we have one computation block per rank. So distributing the computation is quite simple. But what about the data? Let's start with an example. So we have tensor x, which is three-dimensional ijk, and this means that we will also have in this space, we're going to have 8 blocks, and therefore we're going to have one block of x per rank, which is again simple. What happens when the data do not match the dimensionality of the iteration space? So let's look at another example. We have the matrix A, which depends on the variable j and a. And a, as we said, has the size of 1. So essentially, a has to be split into 2 blocks. Now, if we try to make a match with the process and block coordinates, we can see that each block of A could potentially belong to a number of different ranks, like 4 actually in this example, for each of the blocks. So what is going to happen here? The answer is that actually all of these ranks have to get the corresponding block of A. And this is because they need it in order to be able to complete their assigned sum computation. So how we can interpret this in another way is that we have to replicate each of block of A to all the processes that need it. And let's take again MPI. So with MPI syntax, what we will do is create an Cartesian subcommunicator and then do a local broadcast. What about the output? So let's continue with our example. We have the output T1 that is 2D, it's a matrix and depends on I and A. Now, because A again has size of 1, we have again 2 blocks, and again we can see that each block can belong to a number of different ranks. So here again, the block has to belong to all of those ranks. The only difference is that this is not exactly automatically replicated, but after each process completes its subcomputation, it's going to have a partial sum of this block. So what we need to do is we need to reduce all these partial sums together in order to get the complete result. With MPI, we will again create a Cartesian subcommunicator and then perform a reduce and or an all reduce collective. One more thing in order to be able to complete our data distribution. So as we said, we have 2 groups. So from the first group, we got the output T1 that has to be reduced to get the correct result. And now this T1 is an input to the second group. But the problem is that the process grid of each group is different. So the first one is a 4D, the second is a 3D, and they might not be compatible. So if we go back now to the information we got from SOAP, and we also say that we are using 8 processes, we will see that the process grid for the second group is going to have dimensions 2, 2, and 2, while for the first group was 2, 2, 2, and 1. And if we look at them, we will see that they're actually not compatible because in the first process grid, the length for the variable a is 1, while on the second one is actually 2. So this means that after we complete the first group of operations, now the distribution of T1 is not compatible with the second grid. So we need to redistribute. So conceptually, how this happens is that for these subcommunicators that we saw before, we have leaders. So the leaders from the first process grid are going to send the blocks to the second one. So we're going to use this with send and receives. And then the leaders of the second process grid are going to do local broadcast in order to replicate the input data of the group appropriately. The last step of the Deinsum workflow is to automatically generate code that implements our program with the SOAP-derived schedule. So this is done in 2 parts. In the first part, we generate data-centric Python code. So data-centric Python is a subset of Python that is supported by the data-centric framework, and it has some enhancements for HPC. For example, it has an MPI communication interface that we use to generate the Cartesian process grids. For simple operations that do not have contractions like outer and Khatri-Rao products, we generate Python for loops. While for operations where there might be an optimized implementation, we use Python built-in methods or methods implemented by popular Python modules. Like, for example, the NumPy module has an implementation for the Tensor dot operation. We automatically generate code for the MPI collectives like reduce and all reduce. And last, we also implement the redistribute operation for data as described earlier. Now, in the second part of the code generation, we use the data-centric framework to automatically parse our Python code and convert it to a shell library written in C++. So, for example, for loops are automatically converted to C++ for loops, and because they can be executed in parallel, these will automatically use OpenMP for CPU, but it will also generate custom CUDA kernels for GPU architectures. For these operations that for which an optimized library exists, it can also automatically generate code that utilizes them and link against these libraries. So, for example, for CPU, we use for Tensor dot the TTGT approach, which stands for transpose, transpose, gen, transpose, and on the GPU we use the cuTensor library. For MPI, these will generate the appropriate C++ MPI code, which, by the way, can be CUDA aware for GPU architectures. So, time to look at experimental results, and we are going to start with CPU architectures. So, we perform weak scaling experiment on the Piz Daint supercomputer from 1 to 512 nodes. Now, each node on Piz Daint has an Intel CPU with 12 cores, and we are going to compare Deinsum against CTF, the Cyclops Tensor framework, which is a state-of-the-art framework for performing tensor contractions. We are going to measure the total runtime, but for Deinsum we also measure the pure computational time, and by subtracting those two we get an estimation of the communication overhead. Now, in the paper we have 10 benchmarks. We are going to focus here on 3 of them that are representative. We have 3mm, which is 3 matrix implications. We have an MTRP of order 5, so the main tensor has 5 dimensions. And we have TTMC order 5. TTMC is tensor times matrix chain. So this is an operation that appears in the Tucker decomposition. Now we start with a single node execution, and we can see that Deinsum and CTF are approximately equal in performance. This is because both will utilize optimized libraries, so in this case it's MKL. But as we increase the number of nodes, we see that Deinsum scales better. And at the largest scale that we tested, it's about 2.4 times faster than CTF, and up to 16 and 18 times in the other tensor contractions. And now we can see in the 3mm, it's very easy to see that as we scale up, the communication overhead starts to become dominant. So we also did some profiling to see why, and we found out that the bottlenecks is basically the MPI collectives performed on the sub-communicators. Now, to understand a bit better why, we can have a look at the process grid that we generate based on SOAP for 3mm and for the MTTRP kernel for 512 nodes. So for 3mm, it's going to be a grid of sizes 8, 8, and 8. But for MTTRP, it's going to be 11632 and 111. Now, if we look at the specific tiling dimensions that are being involved for the all reduce that is needed to get the correct result, then we will see that for 3mm we are going to have 64 tiles, so we're going to have an all reduce in 64 different subcommunicators, while in the FTTT-KRP it's actually only one tile. So we have to do an all reduce in all 512 nodes together, and this seems to perform better on the machine that we run our experiments. We proceed with GPU experiments, again weak scaling on Piz Daint on the same number of nodes. So each Piz Daint node includes also an NVIDIA P100 GPU. We are measuring the total runtime, but this time we are also measuring the runtime with the data already in GPU global memory. This is to account for the fact that in experiments where the data are too large, the total runtime is going to be dominated by copying from the host to GPU global and back for the output. So we start again with the single node execution, and again we see that Deinsum and CTF are approximately equal, again because both are going to use optimized libraries when possible. But again, as we increase the number of nodes, Deinsum scales better. Now the largest scale is 2.5 faster in 3mm and up to 9 times faster in the MTT-KRP.
Okay, so to conclude, here we present Deinsum, a complete framework that takes an arbitrary input string as an Einstein and first provably minimize the number of arithmetic operations by splitting it to binary contractions, then uses the SOAP model to provably find optimal tiling and kernel fusion, and then using these insights, we generate the optimal parallel decomposition, and using Dei's compiler framework, we automatically generate optimal code that works for both CPUs and GPUs and on a distributed setting. And this automated code outperforms significantly state-of-the-art libraries both on CPU and GPU on all tested scenarios. Finally, the whole code is available open source on our GitHub repository, so please do see the code, and thank you very much for your attention.